All right, let us continue here. We are at a discussion that concerns the problems that inductivism faces. The first point, the first difficulty is the difficulty with condition C2 that demands a variation of the circumstances under which we observe a certain effect, and this variation is endless and therefore not feasible. We don't know what to do. We can vary conditions with no end, and therefore we can never stop this step of variation, so because it's always another step how we can vary conditions. So we don't really know what to do with condition C2. This is the first problem. Now we come to different problems. The next problem is this. The point, that's a proposition that I'm making here, a statement. The observation of facts must be somehow directed. Only relevant facts should be observed. Let us assume that you want to study the growth of a plant or the level of a lake or something. Then the observations you want to make are, of course, only observations that are relevant for the particular thing in question. Of course. I mean, it's not interesting then to know something completely irrelevant, not in any relation whatsoever. So we need some sort of idea of what is relevant in a certain situation. Now, the point is now to which I want to direct your attention that the judgment that a certain fact is relevant for a certain generalization that presupposes theoretical elements. And that by itself is not a catastrophe, but the point is that we started in inductivism with the idea that in the beginning there are theory-free facts. Right? That is the attraction of inductivism, that you say, you know, we start with something that is very secure because we simply observe something and no theory is involved. Therefore, the possibility of making mistakes is very, very, very small, right? No theory. Theories can be false, right? But if I observe, here is a watch sitting on this desk, I mean, I'm on fairly safe ground, right? There's no theory involved, therefore no possibility, or almost no possibility for mistakes. So the point is that the attractiveness of inductivism, by starting with the idea we use theory-free facts, this attractiveness is now in danger, because in order to observe relevant facts, we have to have some sort of element of theory in there, as I show you immediately by an example. Now, before discussing the example, I must reactivate some chemistry knowledge, right? Which you may have forgotten in the meantime, especially the engineers. You don't, oh, you do have something to do with chemistry as well. You all have to do something with chemistry. It's the law of constant proportions, right? The law of constant proportions in chemistry says that chemical reactions always take place in constant proportions, right? You take 2 parts of hydrogen and 1 point of oxygen, and you bring them together, and then it makes boom, right? And you get water, right? Okay? And you have to have a constant proportion. If you take different proportions, it doesn't work, or you get a rest, right? The point is, that's of course quite clear from today's point of view, because there are multiple atoms and they are reacting, and of course it's always a certain number of atoms that form a certain compound, right? It's the law of constant proportions. Now the point is that in the history of chemistry, it was a very deep problem to discover the law of constant proportions. And the background is this. People made observations, and they made observations of what we today call chemical, the build-up of chemical compounds, chemical reactions. But they also observed solutions, say sugar in water. In solutions, there is no constant proportion, as you all know. There are people who drink tea without sugar, and people with a little sugar and with more sugar and so on, and dissolves completely up to a certain degree, right? So in solutions, there is no law of constant proportions, because solutions are something different, as we know today. But the point is that in an earlier period of chemistry, people did not know the difference between solutions and chemical reactions. And in fact, they thought solutions are exactly the same as chemical reactions. Their criterion was whether in the beginning you have two different things, then you pull them together, and then you have one homogeneous thing, right? And they said, this is a certain process in nature, right? One and the same process in nature. And from today's point of view, of course, these are two very different processes, because one is a physical process of going into solution, and the other one is a chemical process of forming a compound. Very different, of course. So the point is, as long as people did not differentiate, make a difference between physical solutions and chemical reactions, they could never observe the law of constant proportions. It was impossible, right? It was only possible to find inductively the law of constant proportions once you said the observations about solutions are not relevant, right? You had to say, these are not relevant observations. Here are all the relevant observations, and then you single out the observations of chemical reactions, and then you can observe the constant proportion of the reactants, right? But you have to know that solutions are something different, you know, sugar in water, for instance. They are something different, and therefore that all the observations of solutions are not relevant for the law in question. So what you see here is the inductive generalization to the law of constant proportion is only possible if they have a criterion of relevance. Namely, what observation is relevant, and then you must have the knowledge, okay, there is a fundamental difference between physical solutions and chemical reactions. And the law of constant proportion, of course, holds only for the chemical reactions and doesn't hold for the physical solutions. And all the observations on physical solutions are simply irrelevant, right? They don't contribute it. They don't contribute because it's a different class of processes you are observing there. And now you see that the idea that you can come by inductive generalizations to the general statements by first observing the facts completely theory-free, that doesn't work. Because you have to know what are the relevant facts, right? And in order to judge whether facts are relevant, you have to have some sort of theoretical element. In that particular case, it's the process of distinguishing between physical solutions and chemical reactions. And as a matter of fact, the discovery of the law of constant proportions was the same process that led to the distinction of chemical reactions and physical solutions. Before, people had a very plausible hypothesis, namely, there are two fundamentally different processes, namely, you have two things, you put them together, and there is one sort of process in which they somehow combine to one thing, homogeneously, and there are other processes in which the two things do not combine to one thing homogeneously. So put sand in water, right? You put sand in water and you have two different things, right? It remains two different things. You say, yes, this is one sort of thing. But if you put salt in water or sugar in water, well, it's one homogeneous thing. Or if you take natrium and chloride together, you get natrium chloride, right? It's also a homogeneous thing. But people didn't know that there were two, from our point of view, fundamentally different processes involved, which are nowadays, of course, distinguished as solutions and chemical reactions. And people had to learn that first. So the point is that the upshot here is that one of the points of extreme attractiveness of inductivism is that, we start with something very secure because it's theory-free. Therefore, there are no hypotheses involved, and we can simply, by observation, look at the facts, and they form the basis of our generalizations. But the disappointment here with that point of criticism is that because we have to make a judgment whether certain observations are relevant or not, theory is involved already there, such that the dream of starting from something extremely secure and then going to the theoretical by inductive generalization, and then, of course, running a certain risk, but we start from something secure, that doesn't work, unfortunately. So inductivism loses, by this point of criticism, loses some of its attractiveness by saying, well, unfortunately, it isn't that secure as it looks, right? And science is somewhat more difficult than it is suggested by inductivism, namely that we can at least start on a secure basis. Even that security doesn't exist, okay? And that's, of course, a criticism of inductivism, because it seemed to be that we have this secure basis, but the fact is we don't have this secure basis, because also the observations are already somehow impregnated with theory. Okay. Is that understandable? You have to think a little, right, in order to understand that. Okay. Okay. Now it comes even worse, unfortunately. It's not only that we have to decide which observations we take seriously in order to justify a certain empirical generalization, and that we need some sort of theoretical element here. It's even so that a singular observation statement is not completely theory-free, right? A very innocent-looking observation statement, also that already involves some theory. And why is that important? Because with theory you can make mistakes, right? Once you have a theory, it can be false, right? Could be false. So even a singular observation statement is not theory-free. This may be very surprising to you when you say, what? Well, I show you. Now look, this is now for the horticulture people, the example. Look at a very, very, very simple statement like, this is a plant of species X. Yeah, you have to have, that's a decision you have to make in horticulture science, right? When you build your observation basis and you say, okay, I need 400 plants of species X, then you have to go through your lab and say, this is a plant of species X, and so on. You have to make a decision, because if you take the wrong plant, of course, you cannot do your observation on that species. So you must be able to make, and this seems to be an extremely, simple observation. But the point is, you're using, when you make such a statement, the concepts of plant and species. And these concepts are already theory-laden, right? There is already theory inbuilt in them. The concept of a plant is already a concept in which there is some theory. For instance, you assume that plants are assumed to be distinct from animals, among other things. I mean, when you talk about plants, you have in the back of your mind, a plant is not an animal, right? There's a difference between plants and animals. It looks completely trivial, but it is not that trivial. Just look at the former example about solutions and compounds. It's not trivial to find the difference, right? And it's not completely trivial to find the difference between animals and plants. And furthermore, there's another much heavier theoretical contribution. You use, when you say this is a plant of species X, the concept of a species. And the concept of a species in biology is not completely uncomplicated. You're assuming, and you have good reasons for that, you're assuming that biological entities can be ordered in fairly well-defined classes, that there is a taxonomy, right? You're using the taxonomy every day in horticulture science and in biology. You're using it all the time, but don't forget, there is a theoretical element in it, because you are assuming something about the tree of life, the ordering of plants, and so on and so forth. So these are not completely innocent concepts. They are concepts that already have a theoretical content. Now, you may say, well, that's right. Okay, yes, there's some theoretical element, but it's harmless, right? It doesn't hurt. And that may be right. I'm not doubting that. I mean, usually in many occasions in the biological sciences, life sciences, whatever biotechnology, of course you use the concept of animals versus plants, and you use the concept of a species, and it does not cause any problems whatsoever, right? Sometimes at some borderline cases, if you ask the question, what's the difference between a variety and a species, you may have trouble, and in certain areas of botany, there are real troubles of finding relevant classes and species. but in many, many occasions it's no problem. I'm not doubting that. What I'm saying is, if you look at the position of inductivism and the attractiveness of the position of inductivism, that attractiveness derives from the idea that we can start science on the basis of observations where it is practically impossible to make mistakes because there's no theory involved, right? That's how I started, observe the theory-free facts. But the point is, once you look at it more closer, you realize, oh, theory-free facts are probably not available at all. Even the most primitive singular fact, singular observable fact, has some sort of theory involved because we use certain concepts, and the concepts themselves could be different ones, right? Could turn out sooner or later that we need different concepts, and therefore there is a theoretical element in it, and there is therefore a hypothetical element, an element that could be false. As I said, it's not an everyday worry, but it's just criticizing the position of inductivism that singular observation statements are theory-free, and they are not. Right? They simply are not. It usually doesn't cause problems, but it's a problem for the position of inductivism. Inductivism should be more modest. It cannot say, wow, science is secure because we start with theory-free facts, wonderful. No, stop, it's not true. It doesn't work that way. It's more complicated, right? And we don't know exactly how to deal with that, but it's certainly a problem for inductivism because it loses some of its attractiveness. Okay? That's plausible. I mean, it may sound to you a little like hair splitting, making a little minor point, and it is a sort of hair splitting, but the point is the hair splitting is necessary in order to show that the position of inductivism is not as strong as it appears. It appears so strong by saying, look, we start with theory-free facts, isn't that wonderful? We know exactly what we are doing. No, you don't know exactly what you are doing because there are no theory-free facts, right? So it's a little more complicated. Perhaps that causes problem, perhaps not, but it's just not true what you're saying, that in inductivism we start with theory-free facts because there are no theory-free facts, right? That's the problem, okay? So let's go to the next point of criticism. Now this is something that has been known for a couple of 100 years, and it does hurt a little. It's something where one says, well, yeah, but what do we do? That's the following, that the justification of the inductive generalization is probably impossible. And that means the following. If someone asks you, are you really justified that you have a large number of observations and you have under varying conditions, you have made these observations, and all the observations are in accordance with the general hypothesis, so you fulfill conditions C1 to C3, and then someone asks you, are you really justified then in going to the general statement? Are you really justified? Is it impossible then to make a mistake? No, it is not. I mean, take the example of the black swans. I mean, you may say, if you don't know anything about Australia, and then you observe the swans everywhere under very different conditions, and you look at them, and thousands of swans, and all are white, and you try to vary your conditions as far as you can, and you fulfill the conditions C1 to C3, and then you generalize to all swans are white, and it's still false. Right? You cannot exclude, by obeying conditions C1 to C3, that the resulting generalization is false. You cannot exclude that. There is no justification that you are absolutely safe when you make the generalization. Right? And that's a little disturbing. I mean, it sounds very, very plausible to do the generalization, but if you look at it very critically, you may say, well, in the end, there is no justification, no final justification. Of course, it's plausible, and we do it every day, and it works every day, usually. But in the end, I mean, there is some sort of gap, and there is some sort of insecurity. And there is no justification that it really works. I give you an example. If you try to justify that procedure, then you mostly end up in circularities, right? That you are already assuming the validity of that step without recognizing. So for instance, that's a very common one. Now, if you say, these inductive generalizations are justified because nature is ordered by regularities, right? If there are regularities in nature, then of course, if nature is, say, organized such that certain, say, birds have a certain color, if that is a regularity in nature, then of course you don't have to look at all the birds, but you look at some of them, enough of them, and then if you are at the regularity, then you have observed 400 of them, and you say, all of these birds have this and that property. And that may be right, if there are the regularities in nature. If you happen to stumble upon such a regularity by singular observations, and then you say, of course, now I generalize, and that's a more or less safe procedure because there are these regularities in nature. And of course, I can be unlucky and not get the regularity. But if I get the regularity, it's okay. And because there are regularities in nature, that's in principle a good procedure. I can make mistakes, but in principle it's a good procedure. But the point is then that you are supposing that nature is ordered by regularities. And how do you know that? What's the basis for that? Well, the basis for knowing that there are regularities in nature, that's that you say, well, I've observed it many times. Okay? But then you are using the same sort of thinking procedure, right? You know inductively that there are regularities in nature, but we need regularities in nature in order to justify the inductive step, and that's a circularity, right? A circularity because you are using something to justify a certain statement. But the statement is about that what you are using. And that's, of course, no good argument. If you say, why is here a computer on the table? And you answer, because there's a computer on the table. Right? That's not an answer, that's a circularity. If you want to give an argument for a statement, you must say something else than the statement itself. But it seems to be here that the regularities you are supposing here, you can ask it in the following way: how do you know that these regularities will hold in the future, which you need in order to have an inductive generalization? If you have a regularity, you say, yes, there are regularities in nature, and I use them when I do inductive generalizations. Then you must be sure that the regularities will stay there forever. How do you know that? Well, we assume that, and we made, it's no problem in science that we assume the irregularities, but you don't really know it. So there is a certain uneasiness about the inductive generalization. Probably all the attempts so far have failed to give a really good justification for this inductive step, and that hurts again. I mean, as I said, mostly it works, but not always, right? There are very bad generalizations. There is a rather black what's the correct word? Sarcastic example. Someone is on the top of a skyscraper of 100 stories, right? And he jumps down and says, 10 stories he flew, no problem, wonderful, no problem. Next 10, no problem. And then he generalizes after 30 levels, he says, no problem, right, I can inductively generalize. Then wait for 100, right? And it's a bad generalization, okay? Right, so it is tricky to generalize. It's very tricky. And it's difficult, it's very, very difficult to justify, in principle, the generalization. And one would like to have that, but that doesn't seem to be possible. Again, one may say, okay, yes, it's not beautiful, it would be better to have a justification, we have to live with it. Yes, indeed, you may answer that way, but the point is again that it weakens the overall position of inductivism. That you say, oh yes, there's something important missing, and you weren't aware that it was missing. This is something which was already made aware by a famous philosopher, David Hume, in the 18th century. He said, look, these inductive generalizations, they are extremely tricky, and one has to be very careful. Okay, all right. I'm not telling you reactions on that now, I'm just listing up the problems that inductivism faces. And this was the fourth problem. Now here comes the fifth problem. And that's a very different story. Now this is something that is really relevant for the practice of science. The other problems are not that relevant for the practice of science, but this is one that's really relevant for the practice of science. If you look at inductivism, and then you observe in scientific life that it's quite often the case that scientists disagree, right? They don't agree about something. Now, if you have a philosophy of science that is a position that tells you what the nature of science is, you know what science is, then one should somehow also understand why is it possible that scientists disagree, right? Serious scientists who disagree. That happens in science all the time. Now, if you look at inductivism, if science consists in making these observations and then generalizing to the general statements and then applying the general statements to particular cases in order to predict or to explain or to make technical applications, then a disagreement among scientists is only possible if at least one of them makes a mistake, right? Because what are the steps? I mean, the steps are you make observations, right? Can you disagree about observations, really? Not really. I mean, if I make the observation, here is a watch on that desk, and you disagree with me, I mean, I guess you make a mistake. It's very simple. Your disagreement about observations can only be on the basis of mistakes. One is right and the other one is wrong. The next step about the generalization, right, when we have a few hundred or a few thousand or whatever is necessary, and then we generalize, then it's a question, and I say, yes, the generalization is possible because I have fulfilled the conditions, and someone says, no, it should be possible to decide that. There can't be a rational disagreement that you say, yes, you've got a good argument, I've got a good argument, we don't know who is right. But there's only one way. I mean, one must be wrong, one must be right. And the same then about deduction when it comes to explanations and predictions and technical applications. It's again the case that it should be possible to really decide. Right? There is no way. The point is that if you look at science, in many occasions, one has the feeling there must be something like a rational disagreement, namely a disagreement between people and no one committed a mistake, right, in science. That it is not the case that it is always clear if you have a disagreement in science that one is just wrong. I mean, if a disagreement between you and your supervisor, you better assume it's you who is wrong, right? But that's a different story, okay? Right? But if it's a disagreement in science, in action, you know, between researchers at a conference, if you always assume you have a disagreement between two, then you say one must have committed a mistake, you know, was sloppy or did not observe carefully enough. That's probably a mistake. It's different, especially if you look at what we don't do here now. If you look at longer term disagreements in science, then it's very often that nobody committed a mistake, but there are somehow different viewpoints. They have excellent arguments for their viewpoints, but they still don't find an agreement. And for such a thing, you know, having very good arguments for both sides, and nobody committed a mistake, and sooner or later it turns out that perhaps both, you know, were not right but didn't commit a mistake. They did everything right, but they didn't know something, for instance, and therefore they came to different conclusions. For this sort of rational disagreement, as I call it here, for that sort of rational disagreement, there is no space in inductivism. Right? There is simply no space. And that must make one suspicious because, I mean, if something like rational disagreement exists, then a philosophy of science that tells you what science is should be able to give you some sort of explanation how that is possible, right? It has to give you a story. But inductivism is so tight, in a sense, that it doesn't give you that room. How serious people who did not commit mistakes, but did serious science, made everything all right, but still disagree. Right? For that is no room in inductivism. And that may shed some doubt on inductivism and say, well, that's very strange, right? That is probably a simplified picture in a sense that we don't have that space for rational disagreement. And that must be somewhere, this space of rational disagreement. And inductivism cannot account for that. And that is, again, it's the sort of thing they say, it's not that plausible, right? When we cannot understand what rational disagreement is in science, then we don't understand something about science. Okay? This is highly implausible. And again, this is not a knockdown argument, but it's an argument that makes you possibly aware, that makes you sensitive for something that a good philosophy of science, a good answer to the question what science is, should be able to address, namely, how is it possible that we have rational disagreement? And inductivism cannot really do that. And finally, and this is an argument which is probably immediately clear to you once I articulate it, inductivism is certainly, now I'm really saying something very strong, certainly not generally valid. And that is because what we have in science, say, at least from the, if you look at science of the 20th century, and you look at the larger theoretical things, and I just take one example. Now in biology, the structure of DNA is something which is everywhere accepted, you know, the double helix structure. Now imagine how should an inductivist, someone who says, yes, science works in the following way, come up with the general hypothesis that the structure of DNA is the double helix. What sort of observations must he make from which he can generalize? No way. Absolutely no way. Today you may, I don't know whether you can with certain forms of microscopy, whether you can see the double helix structure. I don't think so that you can immediately see it, but you get X-ray pictures and so on and so forth. But you need much theory to come to this structure. So when you think of more complicated theoretical elements of science, like the hypothesis that the structure of DNA is a double helix, and then you try to say, from which observations can I generalize to come to this double helix structure? There are no observations from which you generalize, because there are no singular observations of pieces of DNA which show you the double helix structure, such that you have 5,000 such observations. Oh, the DNA of apes, of chimpanzees has a double helix structure, of the fruit fly it has a double structure, of this plant XYZ it has a double structure, has the structure, and so on, and then you generalize, right? But there are no single observations, real observations of the double helix structure of DNA. There aren't any, right? If you look at the story how the double helix structure was discovered, it was, of course, X-ray spectroscopy plus model building, right? So people generalized from something, but certainly not from observations, theory-free observations, no way. And then, straightforward, just by generalizing, having something special and then generalizing, it doesn't work that way because you cannot observe directly, at least you could not at that time, directly observe the double helix structure. You can take other examples. If you take examples from physics, if you take now let's go to the engineers. If you take flow equations, right? If you take Navier-Stokes equations, you need Navier-Stokes equation for flows, whatever. Anyway, any equation concerning water that's more complicated, some flow equation or whatever it is, you cannot observe singular instances of it. There aren't any, right? If you look at quantum mechanics, you don't have to do anything with quantum mechanics. It's a complicated equation. There aren't single cases. So these are theories that are somehow very, very differently generated, like the theory that the structure of the double helix is such and such, right? There are no singular observations. So what inductivism describes is a situation that was really present in 17th century science or in 18th century science. So when people discovered the ideal gas law, pressure, volume is constant, in constant temperature, that was something that could be gained by somewhat like an inductive procedure. Robert Boyle made observations. The guy from the Boyle-Mayotte law, this is the Boyle-Mayotte law, right? He made observations. He measured pressure and volume and then, make a plot and look whether the product is a constant. And then he could generalize and say, yes, every ideal gas has this property. There you have particular instances that you can observe, and then you can observe that and then generalize. Whether it works is a different story, but there it is at least plausible. But if you look at science from the 20th century and also parts of 19th century science, if you look at Maxwell's equations or whatever it is, then it is just not possible because there aren't the single cases from which you can generalize. The step from the observations to the theory, to the general, is much, much longer and much, much more complicated. And it can't be just an inductive generalization. It must be different, right? So it is therefore understandable, intelligible, why inductivism was a philosophy of science that was widespread in the 17th, 18th, and 19th century, because it had some plausibility, right? Looking at laws like this, like this one, P times is constant, or also the law of gravitation in principle, and the law of free fall. There you make singular observations and you generalize. It seems, well, at least roughly to work. It's at least not implausible. But if you look at Maxwell's equations, so the structure of DNA, or Schrödinger's equation, or whatnot, or the standard model of elementary particle physics, or if you look at the Krebs cycle in biochemistry, or if you look at any of these theories, there is no way to say this is just an inductive generalization, because there aren't the simple facts that you can generalize. So the problem is that science has become, within the last, say, 200 years or so complicated that the theories or the general stuff is much further away from the observations. And there's no way that you can get from the particular singular observations to the theories by simply generalizing, because there is much in between. And therefore inductivism is, in principle, certainly not generally valid, because much of the most modern stuff of modern science is certainly not gained that way, because the theories are so far away from the particular observations that no step of generalization simply leads to them. Okay. Now, let me finish that here. Note that the difficulties 2 and 3, I said that already when I discussed them, are not deadly to inductivism. There is the question about theory-free, right? That you need theories already to state which observation is relevant and which not, and that singular observations already have a theory content. They show, however, that a build-up of scientific knowledge from a theory-free basis is an illusion. And that is, of course, an argument against inductivism, that you say, look, this plausibility doesn't exist. Okay, why is this baby so slow now? Okay, it starts to sleep. Thus, inductivism loses much of its attractiveness because theoretical elements enter already at the level of observation. That's what I told you already. And the position dealt with next, deductivism, tries to draw consequences by allowing theoretical elements to enter science at all levels, and by avoiding the inductive generalization because it seems unjustifiable. So this is now the transition already to the next position, which is called deductivism, by telling you, as I said in the beginning, as the program, the next position develops out of the weaknesses of the previous position, right? It develops, people say, okay, this position has certain weaknesses, and we must have a better philosophy of science, a better answer to the question what science is, and that must, of course, avoid the weaknesses and try to deal with them constructively, and that's exactly what's going to happen with the next position called deductivism. It admits, yes, indeed, there is the problem that there are no theory-free observation sentences. We must accept there is always some theory built in, and the step of the inductive generalization certainly doesn't work in general. It is not really justifiable. It's a problem. Let's try to avoid it, right? And the next position will do exactly that, answering the problems here and then developing a new position, and that is where I start next week. So I wish you a wonderful week and see you next week.